Oh, you need the multiple lights.
I think the story was right. He was fighting with Barry.
Oh, I don't. Not really. At least it wasn't earlier. We have.
Oh, the laser point works.
Does it? Okay, so okay, there we go. They get some back. Yeah, so you can use that. Oh yeah. Are you able to give the keys? If you want, use the old fashioned.
Right. Okay. Appreciate it. Okay.
This is what I wanted to say to the university administration every day. And why you has gone totally wrong.
Last time I came here was like COVID. I was like, yeah, I remember I came last February. It was like the 4th.
How could
Maybe we'll
he
start in
have
like
been so brave?
30
This is what
seconds.
is-
Actually, maybe we should just go ahead and get started. Okay. All right. Very pleased to have Carlos Blanco here from Princeton and Stockholm, and he's going to tell us some nice techniques for dark matter direct detection and indirect detection via some molecules, I think, right?
Yeah, amongst other things. Yeah. Okay. So, hi everyone. Last year, like in February, I came here and I gave a talk that was very similar to this. And at that point, we were right at the cusp of putting out a bunch of papers. And so I thought I'd come back and sort of tell you how the story ended and give you an idea of how the saga is progressing. And so I'll move a little bit quickly through the first couple of slides so that I don't just bore you with the same things that I said last year, but then those of you who aren't here, I'll just show that. Okay, so I'm sure everybody here knows this picture, but let me just point this out. This is a very artistic rendering of our stage, and here in blue you have an artist representation of the dark matter halo. Our galaxy is inside, and we are somewhere in like the outskirts of this galaxy. And observations of our of local structures will determine for us two very key things about dark matter. One, they tell us roughly that dark matter is moving with a couple 100 kilometers per second velocities. And they also tell us that the local dark matter density is 0.4 GeV per cubic centimeter. And that's already enough to tell us some key things about how we go about detecting dark matter, right? What this tells us is that the flux increases for lower dark matter masses, and that tells us something about the scarcity of the events that we want to go after. And so in the vast range of dark matter parameter space in mass, you have all the signposts of where dark matter can live, and I'm sure everybody's well acquainted with most of these, and really I just want to call attention to this sub-GeV versus canonical WIMP dichotomy that I have here, and why I think they are fundamentally different, even though the models that produce these things are quite similar. And that's because above 1 GeV, dark matter can excite atoms, and atoms they're interesting, but they're boring because they're spheres, and they really just excite and de-excite in very predictable ways. And so you're looking for these very rare but very energetic events that will light up an entire xenon tank. Whereas below a GeV, you're looking for very feeble recoils, and so that really comes down to detecting single quanta in condensed matter systems. And so that's what I do. I look at things below a GeV. And so
can you remind us, sorry, if it is a fermion, should it be heavier than about what?
So good. If it's a fermion, it should be heavier than about a keV.
About keV. Yes. So you are still fermionic. That's
yes.
Okay.
Yeah. Okay. So good. Yeah. When I say sub-GeV, that's why it stops there at a keV. Okay. Good. So I'll show these pictures, and here's a cartoon of what these exclusion sensitivity curves look like. And really, I just wanted to talk about how one should read these. Okay. So here you have mass on the x-axis and something like a cross section on the y-axis. And generally speaking, you have these exclusion lines that look like these check marks. And what's happening here is that, of course, you have this flux suppression at higher masses. That's why all of these things go linear at higher masses. And then you have both a minimum mass that you're sensitive to, and that's given by the threshold of your detector, what kind of energy transition you're trying to drive, and how deep you go is just set by the rate of your background and the efficiency of your signal. And so ultimately, what we want to do is we want to be sensitive to these benchmarks that can either be, something like freeze out or freeze in, depending on the given model. And in order to get to those places, you need ever smaller thresholds with higher efficiencies and lower backgrounds. And as these things happen, these black blobs will move further down and further to the left. And that's the name of the game. Okay, good. So if you want to go after sub-GeV dark matter, there's some kinematics to keep in mind. So for a particle that's of order MeV, if you're scattering off something like an electron, what you have available to you is something like keV of momentum and order EV of energy. And so you got to look around and you got to think, okay, what systems can I really build that are kinematically well matched to these sorts of interactions? And so it's not too long before you come face to face with this thing. And so this is the rate equation for a lot of these detection techniques. And without getting into the weeds of what's going on, it factorizes basically into three objects. One, the mean inverse velocity that tells you your astro, that tells you what the dark matter velocity distribution is doing. You have the dark matter form factor, which is just a parametrization of like the vacuum matrix element. And here I'm just going to bracket the possibilities between two things, either a contact interaction or a long range interaction. And then finally, you have a transition form factor. And this is where the art of the deal happens. You got to find a form factor for your independent system that is well matched to accept momentum and energy. And it turns out that's really non-trivial. So first, let's talk about the easiest possible thing. Electron recoil, looking for a photon de-excitation. Okay, so I will now just tell you that systems that do this are called chromophores. And what's going to happen is we expect the dark matter is going to come in, it'll excite a virtual state, and then when that de-excites, we're going to get a photon.
Sorry, what are you assuming? That it interacts with an electron?
Yeah, here I'm assuming that
And only with an electron?
It can interact with other things, but right now we're just going to probe the cross-section with the electrons. We'll come back to nucleons later, okay? But this is just easier to start, okay? Okay, so we're going to try to go after the photon signal, and these experiments exist. They've existed for a long time in chemistry. It's called fluorescence, and so what we want to do is fluorescence with dark matter. And this is a sketch of what such an experiment would look like. So something like a 1 liter vial of some chromophore. They're just floating around. The dark matter is going to come in, it's going to excite the chromophores, and then they're going to emit photons. And the photons can do one of two things. They can either be reabsorbed, or they can free stream towards the surface of your detector where you have something like a PMT. And so you got to ask, well, isn't that a problem? Like if I reabsorb, then I'll lose all my signal. Well, here nature has been really kind to us because it turns out that molecular chromophores have their absorption and emission characteristics offset from one another by a Stokes shift. And the probability for self-absorption is proportional to that overlap. And so for some characteristic molecules like trans-Stilbene crystals, you expect 65% of the time you'll be able to free stream towards the surface of a macroscopic crystal. And so this is kind of free that we get from looking at solid state molecules. So that's really wonderful.
So is it 65%? Does it depend on the size of the crystal?
No, it turns out it doesn't. Because what happens is that, say I emit this spectrum, what's going to happen is that it will absorb very quickly in the overlap region, but then the rest is transparent. All of that will free stream.
Is there a simple reason or a way to think about why there's a slight shift between the absorption and emission?
Yes, so what happens is that the excitation occurs between the ground singlet state and an excited singlet state, but it has to excite to a rotovibrational excited state. And then once you lose that rotovibrational energy, and then that's your Stokes shift. That's just selection rules of photon absorption. Okay, so now I'll tell you about carbon, why it should be everybody's favorite atom. Carbons can come together in one of two ways, but the really interesting way is this sp2 hybrid orbital, where you have some axial overlap, and above and below this plane, you have these very delocalized pi orbitals. And what happens is that in these pi orbitals, you have electron dynamics that are very well kinematically matched to these kinematics that we talked about dark matter, they have momentum of order of kV, and they have energy splittings of about an EV. And so naively, we expect that pi conjugated hydrocarbons will be a good system to start off with. And so about 3 years ago, a colleague of mine at the University of Chicago knocked on my door and said, look, we have a vial of this molecule.
Sorry, I'm too slow. KV is what, some vibrational thing or?
No, that's just the momentum. It's the momentum of the electron.
No, but KV energy is, you said, somehow characterizes those particular hydrogen things?
Okay, so good. Let me slow it down. KV is the momentum of the electron, but EV corresponds to the vertical transitions of the electrons. So this is just
So this is really electron levels.
on energy levels.
So
And when
energy
you look at the
electron,
molecular energy levels, they're separated by
but
about
energy levels of electrons, not
Yes.
of vibration.
That's right.
Okay. And EV is meaningful energy.
Yeah, I
scale.
mean, 1 EV is infrared, 2 EV is green.
Okay.
And so if you want to think about it, all I'm talking about is the same kind of excitations that take place in your retinas, right? That's why all the interesting chemistry happens at an EV. It's because of these kinematics. Okay. So we had a vial of this paraxylene compound, and so we sat down and tried to compute these molecular form factors, and what we realized is that there's this interesting kinematic matching. And so we said to our colleague Juan Cuellar, just build an experiment. We expect this to be quite good. And so very quickly he was able to put this together. So this is a 1 liter bottle of ultra low background paraxylene. You put that in some shielding and you take data, and within a few months you have some constraint curves with essentially like garage level physics. This is awesome. This is how science was meant to be done back in the day, right? And so these black lines are where our exclusions were. There's some details there, but again, the takeaway here is that with a few months of data taking in a bottle of what's essentially lighter fluid, we got within striking distance of like really the bleeding edge at the time.
Because why was this chemical? What's so special about this chemical again?
Nothing. This chemical is what they had lying around, and this pi conjugated ring, you can think of it as a delocalized ring of charge. And the energy levels of the electrons flowing in that ring are well separated by around 4 eV.
So it would be easy to scale this up.
It's very easy to scale this up.
Is one doing it?
Well, we're gonna get to exactly where we go from here. Okay. So this was a pilot experiment, and
sorry, Carlos, you have two curves there, where 3.8 hertz and 0.1. Which
Yep.
one was your actual background rate?
so 3.8 hertz was the rate that we captured on the surface. 0.1 hertz was the rate that the PMT was calibrated to deep underground. And so unless there's dark matter somewhere between those two lines, which there's not, the actual background rate that we can go with is this 0.1 hertz.
But this is a fiducial projection. This is not a
That's right.
full run.
Yeah, honest to goodness data is the dashed line. Projection is this 0.1 hertz line. Okay, good.
But you did say, in response, I think, to Andre's question, that was something special about this chemical, this structure, that had a matching between the momentum and the energy. Could you just say that again slowly? Because
Good, yeah.
you also came back and said there's nothing special, but I think you
Yeah, so
didn't mean that.
There's nothing special about the arrangement of the carbon atoms here. The thing that makes molecules like this, molecules that can contain 6-membered rings, is that these 6-membered rings have alternating double and single bonds, and that allows the charge to be delocalized. Okay, and the delocalized charge has momentum, right? The electrons there have momentum, and the momentum is roughly a keV, and so you're kinematically well matched to momentum transfers of order a keV. And if you ask what's the energy levels of these molecular orbitals, they are split by roughly 4 eV. That's all that means. But I can arrange different molecules as long as they have similar structures. They'll have these
That was the
properties.
part I needed
Okay,
to hear
sure.
slower. Thank you.
Yeah. Okay, so we got to the end of this work, and we found, okay, so these fluorescence experiments work, and they're a pretty efficient way to start probing dark matter, and so we can do better. how do we do better? Well, we saw two options. The first option is to reduce background by having some selective excitation. And what I mean by that is if the molecules can tell the difference between thermal background and dark matter, and more importantly, if the signal is different for dark matter and background, then you can do a really good job of making those curves flow further and further down. And so a way to do that is to have a directional detector. And why that would matter is because, well, the picture that I showed initially is incomplete, right? We have a velocity around the galactic center, and that induces a dark matter wind. And if you're sitting somewhere like in a lab in Chicago, and at midnight your detector is pointing up towards the wind, at midday it's actually going to be pointing perpendicular to the wind. And so if your detector can tell the difference between excitations that come from the ceiling and the wall, then you expect a time varying signal. And you can use that to get rid of a lot of background. Okay, so what we needed to do was find a molecule that can do this, and it turns out that that also exists. So this molecule here is called transtylbene. You still have these rings, but now these molecules like to line up, and they all like to face the same way in a crystal. And it turns out that these molecules only like to get excited when dark matter hits them along the edge. If it hits them face on, there's almost a zero probability of an excitation.
What do you mean dark matter?
Sorry?
The molecules get excited not by dark matter, but by your external influence or whatever, right?
Sure. I mean, like you can just calculate what's the probability of exciting a molecular transition.
No, but in actual experiments, you excite them by what? By
nothing. You put them in
by
a very
neutron?
dark room. Huh? What do you mean in an experiment?
No, when you, there is no dark matter as far as we know, right? So you hit it with something, right? So in order to excite it, right?
You mean
When
like to
do the ex-
calibrate?
Is
Like
this a
the
calibration
calibration?
experiment?
Yeah.
Oh yeah, you can do this with a neutron experiment, but you don't even need to do that. It turns out that
Because I'm just curious, right? How can you hit, suppose you want to play with this experimentally, how can you hit an electron with something?
with another electron.
With another electron?
Yes.
So like you put it into a beam, but
That's
one
right.
electron volt electron would not penetrate, I would think.
You're right. So these experiments are called electron energy loss spectroscopy experiments, and they are electron beams of order hundreds of eV, and you look for two things. You look for photons that come from the de-excitation of the molecule, and you look for deviations of the outgoing electron. And the outgoing angle, the term tells you how much momentum you've imparted.
So
So
you actually do have means of exciting electrons.
Absolutely,
there.
absolutely.
Okay.
So the object that I showed you, that form factor, that same object governs electron-electron scattering interactions, and the chemists have a different name for it, but it can be totally reconstructed with experiments.
Okay, great.
And it's anisotropic, right? Like that form factor is very anisotropic, and it doesn't like getting hit face on, and so this is very directional. These crystals that you can form macroscopically know the difference between the ceiling and the wall.
Sorry, I have a really stupid question following what I was asking. So it's good to calibrate your experiment, but can you also control the statement about how this object reacts depending on the direction your dark matter comes from the theoretical computation?
Yes. So the thing that
those things.
So we can do the theoretical calculation using molecular orbital theory, and we can compare it to spectroscopic experiment, and we see that they do match. Actually, last week there was a grad student in Berkeley doing this experiment, but it's also been shown with neutron scattering that these materials are very anisotropic in their excitations. Okay, good. And if you do the calculation, you can also predict what the daily modulation of your fluorescent signal should be. And so that this is what that is. It's the daily modulation throughout a full day for two options, something like a contact interaction or long range interaction. And the thing to take away here is that the daily modulation is huge. It can be up to 70%. This is a very verifiable signal. And what's more is that after a certain mass, if you keep increasing the mass of dark matter, you still expect a modulation because this isn't a threshold effect.
And presumably you can turn your crystal and make this change.
That's exactly right.
Otherwise, you would just not know where
Yeah.
it's coming from.
And-
Because plenty of things happen with the daylight.
And you know the orientation of the crystal axis
With respect to the wind.
I just mean like if I give you a crystal, you can tell me what the alignment of the appropriate axes of that crystal are. It's not like if I have an experiment built out of many of these crystals that could accidentally be misaligned. Like I can look at that crystal and I can be like, this
That's right.
is the side that it will have its maximal sensitivity in
Yes.
this direction. Okay.
So a crystallographer could look at this crystal and tell you, this is the principal axis, and that's how all the molecules are arranged.
Good. Okay,
There's
good.
no ambiguity about that. And you're totally right, you can change the orientation of the crystal, and what that will do is it'll make these waveforms shift in phase, but it'll actually also change the shape of them. So like you see that some of these waveforms have non-trivial substructure, and that's because the molecule has non-trivial substructure in momentum space. And so you can play with that a little bit, yeah.
Sorry, I'm a little confused about what the readout is, like where's the data coming from, the generated flux?
So these are computed, but the readout is just a PMT. You're just looking
Okay,
for
good.
fluorescence photons coming out. You do a photon counting experiment as a function.
Thanks.
Yeah.
Is the photon emission anisotropic?
Well, in these papers, we did not have to assume that, but it turns out that it is in certain materials, and we're actively working on it. So yes, so some materials have emission that is very anisotropic, and that turns out to help you a lot, because then you have to instrument 4 pi. You just have to instrument what you expect the photons to do. Okay, so where does that modulation comes from? It all comes from the transition form factor. If you look at this, this is very similar to something like the in reciprocal lattice of of any crystal. And if you've seen pictures of reciprocal lattices, you know that they can be very different in different directions in momentum space. And so it shouldn't be surprising that if the mean inverse velocity is anisotropic, and that is anisotropic, that you expect these daily modulating signals. And so we verified all of this. And if you put it all together into these sensitivity curves, you can ask, okay, what does it buy you to have these crystals? Well, let's say if you just closed your eyes and ignored daily modulation, where would your sensitivity lie for a kilogram of transtillbene? It would be in these dotted curves at the top. And if you then look for a daily modulation, you gain 2 orders of magnitude for free from going from the liquid state to the solid state. What's more is that you pick up a discovery potential because now you have a falsifiable signal. And so that's what the orange lines are. And what we found is that with reasonable background rates, so these are like ones per minute background rates, which we expect to be the case for something like SNSPDs, a kilogram of transtillbene would already touch these benchmarks in the long-range interaction case. We'll be able to probe it over an order of magnitude. And you might ask, well, okay, maybe these crystals are very expensive or whatever. No, it turns out these are very pedestrian compounds. You could probably find a kilogram of this stuff within a block of this place. So that was kind of cool. And now to the previous point is, what if we don't want to assume just an electron coupling? Well, we can go after nuclear couplings. The story here is very similar, but now you're recoiling against nuclei, and you're hoping that the molecule excites and gives off a photon. And that's kind of not trivial because what you're trying to excite are the electronic states, even though you're hitting the nuclei. And so let's think about atoms for a little bit. So in the atomic case, people that work on the xenon or the argon detectors have been using this thing called the Migdal effect to look for very similar signals, right? And so here what's happening is, in an atom, you can have dark matter recoiling off the nucleus. The nuclei moves very quickly, and so from the point of view of the electrons, you now have a time-varying potential. And you can calculate the probability of going from that non-ground state to being in a plane wave, in an ionized state. And this has gotten a lot of attention, and people have been very successful taking the
And
sensitivity.
this is what is called Migdal effect, that by hitting the nucleus, you actually excite the electron?
Yeah, you ionize
And
the
that's all
atom.
there is to it? It's
Yeah.
called Migdal effect.
Yes, or that's what the dark matter people call it. Most power effect is what a nuclear physicist would call it. But yeah, this is the Migdal effect for, when you see Migdal effect sensitivity curves on dark matter, what they're doing is they're analyzing their data trying to use these probabilities. And roughly speaking, the probability of ionization goes as the mass of the electron over the mass of the nucleus. And this is just a statement of having to donate momentum from the nucleus to an electron. It's just a kinematic mismatch. And so one thing that you can ask is, well, does the Migdal effect exist in molecules? And it turns out, as we discovered last year, not only does the Migdal effect exist in molecules, there's actually
Sorry.
Tell us again what it is.
Because I'm kind of, is it really that trivial? You are saying that to excite, to change the energy level of an electron, I can hit an electron or I can hit a nucleus because of relativity of motion, it doesn't matter. Is it really that trivial?
No. So here you're hitting a nucleus, right? And there's sort of a next to leading order effect that causes electronic excitations. This is very dissimilar from immediately hitting an electron. You hit an electron, that's all, you know.
I'm exciting it.
Right.
Yes.
Here, what I'm saying is that you induce a time-varying potential, and in perturbation theory, you can calculate what the probability is to go from the state that you now
But if
occupy,
the
which is not
resulting
the ground state.
velocity of the nucleus is comparable to the velocity of the electron,
That's right.
But it's not, right? An electron has, it's not. I just don't understand. If you're depositing an EV of energy,
Yes.
the nucleus is not recoiling with
Okay.
so
Good.
why are you saying this?
Right. So here you have to deposit more than an EV, more than hundreds of keV of
Right, an
momentum.
order an MEV or more, I guess.
That's right.
We can do the calculation, so
That's right. So here you have to deposit more momentum, and that's why.
energy,
Well,
well.
no, because this is
both.
this is inelastic. So yeah, you do have to deposit a little bit more energy, but not as much as you think. You do have to deposit more momentum, and that's why Migdal effect curves, sensitivity curves, often take you to lower masses, but not nearly as low as
Could you
direct
just use the
electron
board
recoil.
and tell us what the Migdal effect is?
Tell me what you're looking for.
I think one
The
way
pictures are not helping.
one way to think about it, right, is you have your electrons in a state.
Yeah.
And they're in a bound state, right? So this electron's in a bound state. And then all of a sudden, on a very short time scale, I change what my nucleus is doing, right?
Exactly.
So now I just calculate the wave function overlap of, now I have my bound state electron wave functions, and I just calculate.
The calculation you have to do, but what part of it is Migdal?
I think
Why is he invoking Migdal and telling us?
I thought that was the effect. Now you find something, your old
But
electron.
what is the effect?
Well, I calculate
Just that you have to calculate.
I calculate the overlap of the old wave function to the electron is
No,
in.
I understand the calculation you have to do, but what is the effect?
the change
So
of
the-
the
it's now-
electron
it's now-
state upon
it's-
the change of
It's
the
in an excited
nucleus.
state.
The effect is that the
Right,
electrons,
so what does
you
it
can-
do, practically speaking?
And then the
So
electron
in
falls
atoms-
down and you see it.
yeah. In atoms, you
Oh, it's
ionize
just
the
an
photon.
emission mechanism.
Yeah.
Totally got it.
So this is called the center of mass recoil Migdal effect, most power effect by a nuclear physicist, and it just tells you how to ionize an atom by hitting the nucleus. That's all it is, okay? In molecules, it turns out there's a different effect, and it comes back to something that you were
Wasn't the most
saying.
power effect the recoil of the total crystal, the fact that all the crystal acts as a one body, is that the most power effect? Are there two most power effects?
Yes, so the most power effect that I'm talking about is a situation where you have a radioactive decay, and the back recoil of the nucleus from letting go of a gamma ray causes this secondary ionization. That was the original calculation. But that recoil can come from, dark matter scattering.
Without a crystal.
Sorry?
I mean, of course you are right.
Yeah.
The whole point of Mössbauer is that Migdal doesn't work because all nuclei share the recoil.
Okay, so we're definitely talking about a different most power effect.
I thought most power, I always
Different
discovered
effect
one
or
thing.
different Mössbauer?
Sorry?
No, there was a joke long time ago that most power discovered this thing by chance, but then discovered two.
Yeah, okay.
That is.
So this discussion that you brought up about the Born-Oppenheimer approximation, when do the scales of the velocities of the electrons in the nuclei come into play, well, it turns out in molecules, it totally matters. And that's the reason why you get a second effect, a second way of exciting electrons through nuclear excitations. And so the center of mass recoil is the same thing, right? Think of, you have a molecule, a diatomic molecule, you shift its center of mass, the electrons pick up a phase, and so now you can calculate the probability of them exciting. Okay, the exact same as the atomic case. There's another effect called the non-adiabatic coupling effect, and that comes from essentially a crumpling of the molecule, a relative motion with respect to itself, where the center of mass doesn't move. And in this case, if you account for these effects beyond Born-Oppenheimer, you find that there is a probability of excitation that comes from these situations, and they scale very differently with the masses of the things involved. So the center of mass effect goes as 1 over the mass of the total molecule, whereas this NAC effect goes as 1 over the nuclear mass. And what's more is that they have orthogonal selection rules, so they really are different things. And these things can't, the NAC effect can't exist in atoms. You need a secondary atom to get this going. So that was very neat. And we calculated what, using these processes, what sensitivity would be for 2 toy atoms, carbon monoxide and nitrogen. You would never really use those molecules, but these are molecules that we can calculate exactly on the computer. That's why we use them. And so the solid orange and purple line are the sensitivities that come from the non-adiabatic coupling, whereas the dotted lines come from the center of mass Migdal effect. And as we predicted, because the kinematic scaling is different, the non-adiabatic coupling effect dominates. And this sort of raises 2 questions. One, if this is how good you can do with these, toy molecules, is there a way for you to select molecules that are, well tuned to accept momentum this way? And 2, if we do the calculation of the Migdal effect in molecules this way, we find that we're really rather close to where silicon is for their Migdal-like search. And that made us wonder, well, the silicon people really only calculate center of mass recoil effect. Does silicon also have a non-adiabatic coupling effect? We don't know. We're trying to figure that out with the silicon people. But if that's the case, then the silicon line should actually go 2 orders of magnitude further down.
Can you say why you had an order of magnitude? Because for these, for N2 or something, right, the mass of the molecule versus the mass of the single nucleus is just a factor of 2 different,
There's another factor in there that comes from the selection rules and the fact that these molecules don't like accepting momentum. So it's not just the kinematic scaling. But what this does tell you is that the kinematic scaling is important. So as you go to bigger and bigger molecules, center of mass recoil effect essentially vanishes, and you're only left with the NAC. So how do you find molecules that are optimal? Okay. Yeah. Let me now tell you more about the previous plots, which is that the molecular Migdal effect, because you're crumpling molecules, it's also directional. And so if you do line up molecules, you get a daily modulation, and you get a daily modulation that's still very big. And what's more is that the phase of the daily modulation is dependent on the mass of the dark matter. It's totally not trivial to see why that is, but we're now certain that it is. We've simulated these collisions. And so using these, using molecular crystals, you can run experiments where you can't tell the difference between heavy dark matter and light dark matter, which is not something that could be done before given a signal.
I'm sorry, I'm a little confused. So a question was brought up earlier about the alternative mass matter, where you have something in a crystal lattice and so you don't get this recoil. And so I was with you with this Migdal effect when we were thinking about things like xenon, because we were thinking about liquid xenon. But if we're going to be doing something directional, wouldn't you have to fix it in a crystal and
Yes.
you wouldn't get this recoil?
So that's definitely not true.
Okay.
In a molecular crystal, specifically an organic molecular crystal, the interaction between neighboring molecules sits at totally different scales than the interactions between atoms inside a molecule. And so individual molecules can crumple and can interact very strongly within themselves, even though the interaction between this molecule and the molecule that sits next to it is very weak.
Okay, so you're not disturbing the lattice, you're just disturbing a molecule in the
Exactly.
lattice. Got it.
We're just using the lattice to point them all in the same direction. Okay.
Sir, I don't understand something. How can it be such a big modulation, like 50%? Because I am more or less equally bombarded. The flux of dark matter is more or less isotropic, right?
Well, up to
Because my Earth is only the daily motion of Earth you don't count anyway, so I'm isotropically bombarded by dark matter.
No, it's like
Why do you have
it's like a 20% correction.
it's like an order one boost, right? We're moving 220 kilometers per second in a background of particles.
Oh
that
yeah,
have
yeah, it's
velocity.
200.
And this isn't about the change in the
Right,
absolute magnitude of velocity. It's about the
sorry,
direction.
right. 200 is our velocity, and that thing is like 500, so it's okay.
When you say the phase is mass dependent, you're referring to the fact that it's maximized with the way you've chosen to block this at 12 hours for heavy masses and minimized for lighter
Mean
masses.
velocity
that's
of
right.
dark matter is
Yeah, so-
500. We are moving
so
at
it-
200.
At hundreds of MeV, you get a situation where the amplitude shrinks and shrinks and shrinks, and then it flips in phase and starts growing a little bit. And it turns out the reason for that is that the probability of excitation is a product of two functions that have very dissimilar maxima in terms of direction.
But since Earth
And
rotation of his detector.
we have yet to put out a paper that really gives an intuitive explanation to why this is, but we have simulated it and we know this to be true.
So there's a mass in the middle where there's hardly any modulation.
Yes. And here it's around 200 MeV per lecture. Okay. So how do you look for optimal molecules? So the question is, how do you even know that that this exists? That, you know, these operators that we've written down that correspond to Migdal effect, molecular Migdal effects are real. They're operators that look like that. They're inner products of nuclear gradients. Well, it turns out that chemists have known about these operators for a long time, and these operators, turns out, are the operators that govern situations where you have classically forbidden transitions being optically active in molecules. Okay, so if you look, for example, at the UV-vis absorption of a molecule, here I've chosen toluene, you can kind of convince yourself that the lowest line transition is classically forbidden because this thing doesn't have a dipole moment. Okay, and if it doesn't have a dipole moment, it can't absorb a photon to its first state. That's the selection. And so you should ask, like, if the lower transition is classically forbidden, why do we see it? Well, we see it because it can pick up a very tiny time-varying dipole moment from the vibrations of the nuclei. That probability is governed by the same nuclear gradient. Okay, it's essentially the same thing, and that's why these transitions have vibrational substructure. So all you have to do if you want to select a molecule with a large non-adiabatic coupling, Migdal effect, is look for a molecule where the lowest lying transition is active even though it's classically forbidden. Okay, that's cool. That basically tells us that in molecules, something like a Migdal effect has already been observed and characterized for decades. We're not just spinning plates. This is like these operators are real and observable. However, molecular space is huge. It's unreasonably huge, right? If I ask how many possible molecules can I form from, these 5 elements of less than 11 atoms, it's like 26 million. And if you go up to 17 atoms, it's 166 billion. This is an unreasonable space to just go out and try to data mine. You can do it if you restrict yourself to like only molecules that are crystallizable, that have been characterized in the lab, blah, 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 blah. But ideally, you want to do better than that, right? And so what you need to do is come up with a method to look for favorable properties. So try to look for these properties that can be computed very easily that correspond to maximal dark matter scattering probabilities. and then try to extrapolate or interpolate into new molecules from some finite set of molecules that you've used to train your algorithm. And so this naturally lends itself well to machine learning. And so the method that we're working with now is trying to train networks to learn latent spaces of molecules to do property prediction. Okay? This is something that has been done in chemical literature for some time. And what's more is we're selecting properties that correlate to these maximal signals for dark matter. And once we have a good idea of what some lower dimensional space might be that can give us predictions for properties, we can then sample from that space to generate new molecules.
I think I'm having trouble grasping the words on your
Okay,
plots.
please.
Like, what does 9 atoms complete dash QM9 mean?
Good. I was just about to say that. Okay, so there exists a data set called QM9, and it's a data set that tabulates all of the possible molecules with these atoms up to 9 atoms. Okay, so that's a complete data set. You can feed that into a network, and you can totally characterize the performance of your network. Okay, and that's what we're doing right now. So we're training our network on this QM9 data set, which is complete, and we're trying to ask the question: can we interpolate well in molecular space, and can we try to extrapolate? And if we do that well, can we then move on to data sets that also exist that are incomplete? They don't have all of the molecules, but they have a lot of them, up to 30 atoms. And
Oh, I see. So 30 atoms, but incomplete.
But incomplete.
Got it. Sorry, I didn't
Yeah.
understand. Okay.
Okay, good. And so what this plot shows is that this is a plot that's done yesterday. And what this shows is that we have this this parameter for generating molecules. And what this allows us to do is to start with a subset of QM9. So molecules that sit in a subset of QM9 are red, right? And we can sample from that set. And at deviation equal to 0, we always pick molecules that are there. We always generate molecules from QM9. But as we change this this parameter, we can start generating molecules that are not within the subset of QM9 that we started with. We start being able to interpolate molecular space and to diffuse into places that are missing. And being able to do that is really, really nice, because that means that we can start with a very incomplete set and look for molecules outside of that incomplete subset. And so we think that we can then step up our network and start feeding it these very, very large data sets and really get down to the point where we're really predicting this is a group of molecules that is optimal from first principles.
Isn't it strange that you guys are doing it because somebody must have done it not for some dark matter, but for some medicine or something?
That's exactly right. So we're not inventing these networks at all. We're taking technology that exists for drug discovery and applying it for dark matter detection. And in fact, the grant that's paying for this is an NIH grant for medicine. I think we're the only dark matter group funded by the NIH. Okay. I'll have to keep the rest of this very, very brief. Okay, so going back to option 2, right? So like now I've told you about when you have selective excitation coming from directionality. Now the other option is to reduce background in the emission step. If the emission of your signal looks different for noise than for dark matter, and I'll just I'll get to the spoiler. Quantum dots are these objects that can produce pairs of time-correlated photons if they're excited in a certain way. And so we want to move in that direction. But first I have to tell you what a quantum dot is, right? Consider an infinite crystal of some semiconductor. So here you have lead sulfide. In an infinite crystal, the electrons behave like plane waves modified by some block wave function that tells you about the microphysics and the symmetries in the crystal. But if you take that infinite crystal and start pulling in the boundary conditions to where the size of the crystal is on the order of the wavelength of an electron, those electrons no longer live in plane wave states. They now live in bound states times a block piece. And diagrammatically, what this corresponds to is that if you start with a continuous valence and conduction band in your infinite crystal, as you quantum confine, as you start pulling in the boundaries from infinity, you start being able to resolve the band edge states if they become singular states, and you increase the gap of your semiconductor. And it turns out that that effect is entirely governed by the characteristic size of your quantum dot. And so as long as you can control the size of your quantum dot, you can control how well separated the band edge states are. And so a natural question is, how well can we control that radius? It turns out very well. The private sector has really perfected the art of making quantum dots of arbitrarily precise radii. And so this is a CAD rendering of what a quantum dot is. It's a finite crystal. It's covered with this molecular hair that does not interact at all here. That just allows you to pull huge numbers of quantum dots into suspension, into a solution. Okay, so what's going to happen? Well, it turns out in quantum dots, it didn't render properly. So in quantum dots, what happens is if you strike an electron in a quantum dot and you're exciting an electron from deep in the valence band into deep in the conduction band, creating a very hot electron hole pair, that electron hole pair will very quickly de-excite by several means. It can either emit phonons or do all sorts of things. But one of the things that it can do is it can trade its energy to generate more electron hole pairs. Okay, this is called multi-exciton generation, and it turns out this is very efficient in quantum dots for various reasons. And so once you have multiple excitons at the band edge, they can quickly radiatively recombine and give you coincident photons. It turns out also that the destruction of these band edge pairs is very efficient when you have more than two. And so at the end of the day, you can either have one exciton at the band edge, single photon, two excitons at the band edge, two photons, and that's it. Those are your two possibilities. And so we're looking for a situation that just gives us two time coincident photons, and the time coincident is within the radiative lifetime of an exciton, which is hundreds of nanoseconds. So what does the experiment look like? It's very similar to the first experiment I showed you. It's a vial of fluid filled with quantum dots, with a macroscopic number of quantum dots. But instead of one PMT looking at this vial in the dark, you have two PMTs, and you're looking for these double bang events. And you can then ask, well, what's the probability that thermal noise can mimic this from self-exciting these quantum dots? It turns out to be almost negligible at these scales. So these are our sensitivity curves, and there's a lot going on here. So there's two possible scales that we've identified in which to deploy these quantum dots. A very benchtop scale where you're really instrumenting just 10 grams of quantum dots, which is 1 liter volume. And at that scale, the background rate, so this is the difference between the solid line and the dashed line, really doesn't make a difference because the thermal background rate will just never produce these time correlated photons. And so you can very much characterize your entire detector at this scale. You can then scale up by a factor of 10. And once you do that, then it does make a difference what kind of background rate you have. And so if you use very good PMTs, you can, with 100 gram year exposure, really beat everything else in the market right now. And so we were really excited about this. And there's another thing that you get for free, which is an absorption sensitivity. So here we have sensitivity to EV scale bosons that are absorbing onto the electronic states of the quantum dots. And again, the sensitivity lines are colored in the same way, but you'll notice that these lines are very jagged. And the reason why these lines are jagged is because these are calculated from the honest to goodness optical data of quantum dots. So in some sense, this is pre-calibrated sensitivity projections, right? We didn't need to calculate anything about form factors, nothing. This is just measured data. And so this is something that you get for free for making these detectors. Okay, so we put this out, and this generated some interest from some very nice people in Stockholm, and we formed a collaboration called the Quadra Collaboration, and the idea is to instrument these things with next generation PMTs that are right now being developed for xenon. They're called abalone photodetectors. And so this is a CAD rendering of what the detector is going to look like. We're going to have PMT, so this is like the top shell of the setup where you have 7 PMTs looking at 7 vials of quantum dots, and then an equivalent assembly on the other side, and it's going to be deployed in 2 stages. The first stage is going to be a calibration stage that's going to take a couple of years, and after that, scaling up to 100 gram-year exposure. We should have that within 5 years, we hope. And then we'll have one of these leading edge constraints. We're very excited about this. Okay, so in the last 5 minutes, I'll tell you about what we're now developing, which are hybrid detectors. How do you bring these 2 technologies together? It is very, very exciting. It turns out that initial excitations in molecules can migrate and multiply and attach themselves to quantum dots. Okay. The reason why this is interesting is because, like I told you, excitations are selective in molecules, and emission is selective in quantum dots. So you can have a multiplicative effect in background subtraction if you're able to couple these 2 things together. And what happens is that an initial excitation, if there is a third state that sits in the middle, can fall apart. And from a singlet initial singlet excitation, you can end up with 2 triplets that respects all of your selection rules. These triplets can diffuse through your material, and if that material is doped with quantum dots, those triplets can absorb into the quantum dots. And inside a quantum dot, you're in a situation where you have very strong spin-orbit coupling, and that means that you can radiatively de-excite triplets, which is totally forbidden in molecules. So, you put that all together and you end up with a directional detector that gives you time-correlated photons. And this is the multiplicative projection curve, where the black and the red lines is what you would naively expect from these sort of next generation quantum dot and solid still beam detectors. If you're able to put them together, this would just be such a boon for our effort. And so, expect this in a couple of months. We're very excited about this work. It also turns out that this type of technology is garnering a lot of attention from the private sector because the same.
Shit.
Sorry? Okay. It turns out the private sector is very interested in this type of technology because this is one of the few ways to break the Shockley limit of photo absorption from solar spectrum, right? So solar cells, a single silicon solar cell, has a fundamental quantum efficiency limit of 36% or something like that. If you're able to multiply charges and maintain high fidelity, you can break that limit very significantly. And so there is a lot of really great science and calibration behind all of this, and something that the dark matter community can get essentially for free by knowing a chemist. Okay, good. So I have 5 minutes left. I can either tell you about indirect detection or we can move to questions.
Just do what's more interesting.
Got it. Okay, beyond direct detection. All of these techniques kind of depend on having a volume of molecules that you can put in your lab and you can observe. But you can kind of do the same thing if your volume of molecules is in space, as long as they're clean and they're cold. And so you got to ask yourself, do large vats of cold, clean molecules exist in space? They do. They're called cold giant molecular clouds. And this is a picture of what one looks like. This is real. They look like inky black spots in the sky, where a dense cloud of hydrogen is absorbing all of the optical and infrared photons that come from behind them. And if you observe these things, you can say things about what possible excitations can be going on inside them. Okay, so this cloud Circinus has the density of around 100 atoms per cubic centimeter, and that cloud, because it's so opaque, absorbs all of the photons near its surface. And at the core of this cloud, you end up with extremely clean ground state molecules. And the only thing that disturbs them are cosmic rays. Cosmic rays are the only things known to ionize these clouds. What's more is that you can keep track of the ionization rate in these clouds by looking for molecular tracers. Okay, and we've done that, and we've determined very cleanly what the possible ionization rate in these clouds might be. And so one can ask, Well, now that we've been able to write down what dark matter can do to molecules, let's just try to derive bounds on dark matter interaction with these molecular clouds in a situation where the dark matter is driving an extra ionization.
Do they look at such things with some ALMA or whatever, with some whatever, 300 gigahertz, some such thing?
I don't know. I imagine
Right,
so.
because you would imagine that even though in the optical there is nothing, maybe there is something in radio.
Oh, yeah, sure. Yeah, so these things are not rare at all. They're kind of all over the place, and they're observed by all sorts of telescopes, and they're really only just opaque at the energies where molecules get excited. And so in radio, they should be fairly transparent, and deep in the UV, they're also a little bit transparent. Deep into the IR, they're also a little bit transparent. So that's how you characterize the optical level. Okay, so when can these things probe dark matter in an interesting way that can't just be probed on Earth? Well, in a situation where the dark matter is strongly coupled to the standard model, you end up in these, sensitivity curves. If you're living way up in cross section, you actually reach cross sections where direct detection experiments are no longer sensitive. And the reason why is because those dark matter candidates would never make it to the surface of the Earth. They would scatter in the atmosphere. Okay, and so as a function of the strongly coupled subcomponent and the cross section to something like an electron, you see that in direct detection experiments have this limiting cross section above which they lose sensitivity. Balloon experiments are a little bit higher because they have less overburden, and satellite experiments are even higher. But they all kind of die out at some point, right? The other thing is for 100 MeV dark matter candidates, the CMB, which is the thing that really kills strongly coupled components, loses all sensitivity when you have a subfraction of dark matter that's strongly coupled. That really just represents a small change in what the standard model energy density would be. And in that case, there is a white window up there, circled in red, that is unconstrained. If you then do the analysis of ionizing molecular clouds, you find that that window essentially goes away.
So it's not the dark matter, but some small component.
Yeah, some small, strongly coupled subcomponent.
Are there any viable models that live there besides military?
I don't think so. I don't know. I haven't tried to model build them. This is very recent. We haven't really sat down and tried to cook up models that can hide here. But now we can say, well, now we don't even have to bend over backwards because it's not really even all that possible to hide them there. And in the canonical parameter space, that white window that opens up is roughly up there. The black lines are where the molecular cloud bounds would now sit, and so that kind of goes away for a subcomponent that is about half a percentage. What's more is that you don't need a direct electron coupling because now we've described the molecular Migdal effect, and so you can ionize these molecules via nuclear scattering, and so you can make the same plot for proton couplings. And there the constraints are even less. And really the molecular cloud analysis using the molecular Migdal effect is really the only thing that exists for the strongly coupled regime. And so we're very excited about this. Our grad student right now is finishing editing, and we expect to post this week. So keep an eye out for that. Yeah, molecular Migdal effect in space. To our knowledge, this is the first thing that's been done. Okay.
So these are really big cross sections, right?
Extremely big cross sections.
So this is something with a mass of like the one of the pion, right? 100 MeV, and with a cross section which is bigger than the Fermi scale, the size of a pi square. So these are strongly coupled. Strongly coupled in terms of QCD. These are just coupled. This is the cross section. The size of a proton is 10 to the minus 15 centimeters. So is this even satisfying in parity?
I can imagine a situation where instead of having a fundamental particle, I have something like a cue ball, whose geometric extent places its cross section up there.
These are very low momentum. These are very low momentum scatters, right?
Yeah,
So-
that's way, yeah, I understand.
No, but no, I mean, I'm just saying that you know, like your unitarity arguments for 2CD would be assuming.
But he can still talk about the bounds, even if there's no
Sorry, I'm
model
not
that can.
entirely sure.
Yeah, I
I
mean,
mean,
I-
but 10 to the minus 18 is certainly a
Thompson's-
number that
Thompson
I've
cross-sections.
encountered for.
Yeah.
yeah.
Thompson
absolutely.
cross-section.
But
I-
is there a way you can, like, let us see what would be where would the
Yeah, the
bound
electron
be?
is any big.
How much do cosmic rays contribute in this plot? Can you?
Yeah,
I just worry because estimates are really uncertain.
so uncertainty from cosmic ray measurements are that the black solid band is like the most pessimistic estimate to what those uncertainties are. Right, so the uncertainties are can be quite large if you are so conservative that you almost close your eyes to some recent data, but that's what the uncertainty would be from cosmic ray measurements. And these constraints don't come from seeing like how much you can add to cosmic ray ionization. These constraints come from how much ionization does dark matter need to supply to overshadow cosmic rays. And so because we wanted to
basically you're
sidestep
saying
that conversation.
In that 10 to the minus 22 region, cosmic rays are presently kind of contributing at that level.
Yeah,
But how can you have dark matter with cross-section 10 to minus 22? It wouldn't be collisionless.
Yeah.
It would collide, it would collapse.
well, okay, so there are some strong bounds. The strongest bounds of this like very strongly coupled regime in a situation where all the dark matter is this way come from situations where you effectively donate momentum.
Well,
into the
F
signal.
is the fraction of dark matter?
Yes.
Ah, come on, this is cheating.
Well, I mean, like, look,
But see, these are not soft cross-section, these are cross-section where you bounce off, so here.
I mean, you might say that it's cheating, but the papers that were written from like the CMB, right, ruling out strongly coupled
They
components,
do include this F, I understand.
They were very worried about what happens when the F gets small, and we're saying it doesn't
Right,
matter.
right,
Like, we ruled out by a bunch of things, including the dumbest thing that you
Everybody
can
is
do.
cheating, I agree.
Okay, so yeah, that was the last thing.
Oh, really?
Any final questions?
Yeah, right.
Edmund, so for the second part of your talk where you're reducing the background from its coincident photons, does it suppress all of the backgrounds? In particular, does it also suppress radioactive or cosmic muon backgrounds, or just instrumental
So
things?
it will suppress any background that has Poissonian statistics or anything that looks through. You still have to shield this thing. You still have to do vetoes for muon stuff. And to get rid of radioactive decay, you really just have to get rid of anything in your time bins that has more than 2 photons and less than 2 photons. And radioactive decay, because it's sitting inside a scintillator, would light the whole thing up. It wouldn't be close. You're really only sensitive to like the very, very tail end of beta decay, and that is such a small correction to all the other backgrounds that we didn't think about it much more than calculating how much sits there.
So for the slight particles, for the slight particles, are you going to be champions or you are already champions in terms of putting the bounds?
Not yet. We're going
Because
to
you are probably not the first people on Earth to do this, right?
to do what?
To put limits for this very light dark matter.
No, we're not. Right now, the most sensitive experiment is Sensei, and that is a silicon-based CCD experiment. And they are sort of the gold standard. It turns out they can do very magical things with silicon, and so those are the bounds to beat. And we will do better than silicon imminently.
But won't they do better than that
Yes.
soon too?
Yeah, we basically, so pound per pound, or kilogram per kilogram, molecules can do equally well than than silicon for producing visible signals, right? And so the question is, can you really scale up beyond a kilogram of skipper CCD? We don't know. I'm not sure that would be the most efficient way to do it. And what's more is that if you have a way to instrument that many skipper CCDs, that's kind of what the molecular program needs, right? Like we're limited by the background rate of a photodetector, and the skipper CCD is the best photodetector in the world. And so we're talking right now with Javier Tiffenberg about using some of their old prototypes to instrument the surface of some of our scintillators. And so in some sense, they're really complementary.
Sorry, I didn't understand. So the particle data book will list your bounds or will it not?
I think it will be. Yeah.
Ultimately, but not yet.
You guys are like the xenon to their CDMS.
Yes.
If I want to be like
yeah.
historical. The CDMS didn't scale, but xenon does, because it was a big vat of stuff.
Right, let's thank Carlos again.
Are you saying you can go out and
All I'm
like
saying
mail
is
order
that-
some quantum dots?
Yeah.